this video we're going to perform another experiment with benzyl. We prepared this using the procedure we covered in a previous video. Take a look at that for more details of how to make benzyl. We recrystallized the product from hot ethanol, and we've got 5 grams here of pale yellow fluffy benzyl crystals. Here's our setup for the reaction. We're using a 250 ml flask equipped with magnetic stirrer and sitting on a hot plate. We're going to need to reflux the mixture, so we've a condenser setup ready. Here's our solvent for the reaction. We're using 40 ml of absolute ethanol. You can also use 95% ethanol as well if you want to. Let's first get the ethanol into the flask. And we'll dial up the stirrer. Now we add our 5 grams of benzyl crystal. Here we go with all the benzyl added. It won't dissolve immediately as it's going to need a bit of heat. Here's our next reagent. We've weighed out 2.9 grams of urea crystal. This is a 2 times molar excess compared to the benzyl we added. Let's add this to the flask as well. Okay, we've now got benzyl and urea in here, plus our ethanol solvent. Now we're going to start heating the mixture gently in order to help the solids dissolve. While this is happening, we'll prepare our final reactant. Here we've got 3.8 grams of sodium hydroxide. This is a 4 times molar excess to the benzyl. And we're going to dissolve this in 10 ml of water. As it dissolves, the solution will get pretty hot. But after a few minutes you should have a nice clear strong solution of sodium hydroxide. Let this cool slightly, and then we're ready. Here's our warm ethanol mixture in the flask. We've got some nice needle-like crystals of urea forming on the glass, as you can see. Okay, now we're going to add the sodium hydroxide solution to the reaction mixture. Immediately on adding, the dark brown color is formed. And after a few seconds the mixture seems to solidify into a thick slurry of crystal. Interestingly, none of the procedures we read said this would happen, but we assume this is an intermediate compound forming. We've set up the condenser and we've now turned up the heat so that the mixture can reflux. This starts fairly quickly. Pretty soon the solid slurry redissolves and forms the dark brown solution. And over the next 10 minutes or so, the color of the solution slowly changes to a lighter brown, then to orange, and then finally to yellow. Okay, we've got the reflux going on now, so we're going to let this continue refluxing and stirring for an hour from this point. The color of the mixture doesn't seem to change from this point now. If we stop stirring for a second, you can see that there are some black particles in the mixture, and also what looks like some fine white precipitate. Okay, let's leave this reacting, and while it does, let's have a closer look at what's happening in this reaction because it's quite unusual. Benzyl contains two ketone groups, which are pretty reactive species to nucleophiles. With the hydroxide acting to deprotonate a hydrogen on the urea nitrogen can then attack the ketone carbonyl to form an intermediate compound. But then exactly the same thing can happen on the other nitrogen of the urea with the other ketone group. This produces a compound containing the 5-membered ring, as you can see. But what then happens is a rearrangement reaction, very similar to the one that occurred in the previous video when we made benzoic acid. One of the benzene rings jumps over to the adjacent carbon, and our product is formed. Although the proton on the nitrogen is quite acidic due to the effect of the two adjacent carbonyl groups, and so what is actually formed in our reaction mixture is the sodium salt. Just like in the similar benzoic acid rearrangement, it looks a bit weird, but it is what happens. Okay, here's our reaction mixture 1 hour later. Looks pretty much the same. We're going to stop stirring now, and we'll let this cool down a bit. As it settles, you can see there's some white precipitate in the bottom of the flask. First we measured out 10 ml of water. And we add this to the flask. We've still got some precipitate in here, which must be some organic reaction byproduct. We'll first need to remove this, so set up to filter. Here's the filtered white stuff. Actually not very much in reality. We're not sure what this is, but it's definitely not our product, so we'll discard it. Here's the filtrate, which contains the sodium salt of our product in solution. To get it out as the protonated acid compound, we need to acidify this solution. Here we've got about 10 ml of concentrated hydrochloric acid. We're going to add this dropwise to our filtrate. As the acid goes into solution, you can see some crystalline solid produced temporarily. With swirling, this goes back into solution due to the excess sodium hydroxide present. Some of the urea has hydrolyzed in the alkaline reaction mixture into ammonia, causing the white clouds in the presence of hydrogen chloride. After about 6 or 7 ml of acid are added, the mixture becomes a mass of crystal. Let's check the pH of the mixture. Nearly neutral, but there's a risk that there's still some of our product in solution as the sodium salt. So we'll add a little bit more acid. Suddenly the clouds of smoke have disappeared. Let's check the pH again. Strongly acid. So we're finished with acid addition now. Cover the beaker and we'll let this chill now for a few hours in order to make sure all our product crystallizes out. And once this is done, set up to filter, this time to collect the product. Wash the beaker with a small amount of cold water, and then use this to wash the crystals in the filter carefully. The product takes quite a bit of drying, so you want to break it up and leave it on the filter for an extended period to get it completely dry. Here's our crude product. 4.3 grams of phenytoin as a fluffy dry pale yellow solid. This is a 72% yield on starting benzyl, which isn't bad. If you want a pure product you can recrystallize this from hot ethanol, but we're going to leave ours as is until we can think of a good use for it. Phenytoin was formerly used as an anti-epileptic drug to control seizures, but is no longer widely used. But we don't recommend eating it. It's got a lot of side effects and won't make you feel very good. But this is an interesting reaction because we've synthesized a new heterocyclic ring containing 3 carbons and 2 nitrogen atoms. And knowing the various ways you can create different rings is a very important part of organic synthesis. Thanks for watching, stay tuned, and wishing you a happy new year.